Hi, Assalamualaikum to Dr. Hafiz and everybody. Today we're gonna present about our assignment. The title is System Modeling and Analysis. For subject control principle, the code subject is BERE2363. We are from group 2, section 2/2 BERE. For introduction, I will pass next to Akmal.
Assalamualaikum and good day everyone. Our project is about analyzing a fault at the electrical network using two different methods, which are the frequency domain method and the state space method. The frequency domain method uses the transfer function of the circuit, while the state space method represents the system using matrix and the state variable. In this project, MATLAB used to verify the mathematical model and observe the circuit performance. By using MATLAB, we can analyze the system response and compare the result of both methods. The objective of this project are as follows. First, to derive the transfer function of the electrical network, which is the ratio between output voltage and input voltage. Second, to analyze the transient response parameters such as rise time, settling time, and overshoot. We should evaluate the stability of the system by checking the poles of the transfer function. Third, to convert the transfer function into state space representation. Finally, to compare the performance and validity of the transfer function model and the state space model using MATLAB simulation result.
Hi, Assalamualaikum everyone. My name is Muhammad Aiman Akil bin Muhammad Azriq. My matrix number is B1225101168. So today I will be presenting about the part A, which is I will cover from part A introduction, part A objective, part A circuit parameters, part A calculation, and lastly part A MATLAB coding script and command Windows output and the graph. Okay, so I will start with part A introduction. So control systems are widely used in engineering application to analyze and predict the behavior of dynamic system. Mathematical models such as transfer function and state space representation provide useful tools for understanding system characteristic and performance. In this assignment, an electrical network consisting of resistors, inductors, and capacitors is analyzed. The transfer function of the circuits is derived in the frequency domain and subsequently converted into state space representation. MATLAB is employed to verify the theoretical calculation and investigate the system response. So we will moving on to the part A objective. So there is five objective on this assignment for part A specifically. So the first objective is to derive the transfer function of the electrical network circuit. The second objective is to analyze the unit step response of the circuits. The third one is to determine the poles, zeros, and stability of the system. The fourth one is to convert the transfer function into state space representation, and lastly, to compare the transfer function models and state space model. So next, I will explain about the part A circuit parameters. So for capacitor 1 and 2, we will use the same value, which is the 2.2 microfarad. Same goes for the inductor L1 and inductor L2. We will be using 68 microhenry. And for the resistor R1, we use 4 ohms. R2 we use 5 ohm, and R3 we will be using 6 ohm. Okay, so next for the part A calculation. So as you can see, for this mathematical modeling section, the first step we took was converting the circuits into the frequency domain. So we changed the inductor values to Ls and the capacitor values to the fraction, which is 1 over Cs. So in the step 2, we apply Kirchhoff voltage law using match analysis to obtain the voltage and current equation for all three loops in the circuit. So from this equation, we organize them into 3 by 3 independence matrix. So as you can see on the main diagonal of the matrix is represent the total impedance in each loop. The negative term around it represent the shared components between the loops, such as inductor L2 and resistor R2. So for the step 4, my main objective is to obtain the transfer function by finding the output voltage across capacitor C2. So to achieve this, we need to calculate the current in the third loop, which is I3, by using Cramer's rule. Okay, and then we separate the matrix calculation into two sections, which is numerator and denominator, and perform the cross multiplication operation algebraically. So once we obtain the current I3, we multiply it by the impedance of the second capacitor, which is 1 over C2S, to get the general formula for the output voltage. So in the final phase, we substitute the variable with the actual components value assigned to group 2. So we insert 4 ohms, 5 ohms, and 6 ohms for the resistors, 68 microhenries for both inductors, and 2.2 microfarads for both capacitors. So after simplifying the equation and eliminating the S fractions, we successfully obtain our final transfer function. So by looking at this is a fourth order system, as indicated by the highest power of S in the denominator, which is being S to the power of 4. So this accurately represents the 4 energy storage component present in our original circuits. Okay, next for part A, MATLAB coding. So as you can see, here's the coding that I use. Later in the video, I will explain each command for this coding. So right now we'll be looking at the MATLAB result in the command windows. So as you can see, we get the rise time here, the settling time, and also the percentage overshoot. So next is the unit steps response graph. So by looking at this graph, you can obtain the first one, which is the rise time, and then the second one is the settling time. So this is the pole 0 maps. Okay, next, back to the coding. So for each command, I have wrote the function of each command. So the first one is tf num_den, which is meaning by transfer function, numerator and denominator. So this creates the transfer function model from numerator and denominator coefficients. So the next is figure commands. This open the new windows to display a graph. The next one will be step SYS. This plots the output response when the input is unit steps. So next command is step info SYS. This command is to calculate rise time, settling time, peak time, and overshoot. Next is display. So this display command displays the calculated values directly in the command windows. The next is pzmap SYS. This command is to generate and plots the pole 0 maps of the system. Next is pole SYS. This extract the exact numerical location of the system poles. And the last one will be 0 SYS. This extracts the exact numerical location of the system zeros. So lastly, for part A MATLAB observation. So the electrical circuits contain 4 distinct energy storage elements, which is 2 inductor, L1 and L2, and 2 capacitors, C1 and C2. So by looking at the unit step response graph just now, the system reacts very quickly. The rise time is only about 53 microseconds and is completely settled in just 88 microseconds. So the maximum percentage overshoot is also exceptionally low at only 0.18%. So this happened because the resistor value we choose provide a strong damping effect which stop the circuit from oscillating too much. And for the stability analysis, our pole zero map show that all four zeros are located strictly on the left half of the S plane. So since there are no poles on the imaginary axis or the right half plane, we can confidently conclude that this electrical network is definitely stable. So that's it from me for part A. So I'll be passed to the next presenter to explain about the part B. Thank you.
Hi, my name is Muhammad Haris Aiman bin Erwin. My matrix number is B122510159. For my part, I will explain about part B, which is the state space modeling and analysis. Okay, so basically part B is asking us to change the same transfer function from part A into another form called state space representation. We are not deriving a new circuit equation in part B, but we only convert the equation from part A. As you can see from the result, we convert the equation from part A into a form x dot is equal to ax plus bu and y is equal to cx plus du. Okay, for the first step is arrange the transfer function in standard form. For fourth order transfer function, write it as a gs is equal to b3s power of 3 plus b2s squared plus b1s plus b0 divided with s power of 4 plus a3s cubed plus a2s squared and plus a1s and then plus a0. After set the transfer function into standard form, we need to compare with the transfer function. First of all, we need to find the denominator coefficient, which is we have a3, a2, a1 and a0. And for the numerator coefficient, we got b3, b2, b1 and b0. This system is fourth order because the highest power is the denominator is as the power of 4. Therefore, we need 4 state variables. Next step, define the state variables. So for the phase variable, or we call it controllable canonical form, which is defined as x1 is equal to y, x2 is equal to y dot, and x3 is equal to y double dot, and x4 is equal to y more to 13. And this means x bar 1 is equal to x2, x bar 2 is equal to x3, and x bar 3 is equal to x4. The last equation, x bar 4, comes from the fourth order differential equation. So you get the transfer function is equal to ys over us. Ys stands for b3s power of 3 plus b2s power of 2 plus b1s plus bo divided with us. Us is s power of 4 plus a3s cubed plus a2s squared plus a1s plus a0. And then we do the cross multiply. By the crossing into multiply, we can get we need to convert it into the time domain, which is y is equal to 4 y power of 4 plus a3 y power of 3 plus a2 y double dot plus a1 y dot plus a0 y is equal to b3 u power of 3 plus b2 u double dot plus b1 u dot plus b0 u. So after we get the convert into the time domain, we need to using the state variable. The final state equation becomes x dot 4 plus is equal to negative a0 x1 minus a1 x2 minus a2 x3 minus x3 a3 x4 plus u. This is why the last row of the matrix A contains the negative denominator coefficient. So looking to the right, after we got the state space matrices, we need to substitute the value, which is right here. Substitute the value for x dot is equal to ax plus bu, which is we use matrix A and matrix B, as you can see right there. And then substitute for y, inform y is equal to cx plus du. We use matrix C and matrix D. Then we got the final matrix equation, which is x dot is equal to x plus bu for the first one. And then at the end, we get y is equals to cx plus du. That's the matrix. Then we got the coding right here, the MATLAB coding. So every coding have its function, such as this one, step response characteristic. I will explain it after this. And we got the MATLAB result in common windows. Common windows, we got the matrices result, matrix A, matrix B, matrix C, matrix D. And from the coding also, we can get the characteristic for rise time, settling time, peak time, overshoot, and steady state value. This is the MATLAB result, the unit step response of the state space system. You can see the graph. From the graph also, we can get the rise time, settling time, and final value. So from the code showing before, this is the MATLAB command, and it have a meaning and function. For transfer function numerator and denominator is to create the transfer function model from numerator and denominator coefficients. And the second one is SS SYF underscore transfer function TF, convert the transfer function model into an equivalent state space model. Next, for the matrix, to display the matrix, we use the code SYS underscore SS dot matrix. Same goes to B matrix and the matrix of C and the matrix of D. And then step SYS underscore SS is the meaning of plots the output response when the input is a unit step. And then for calculating the rise time, settling time, peak time, and overshoot, we use the command step info SYS underscore SS. And then to calculate the final steady state output value, we use the command DC gain SYS underscore SS. There you go for part B. And the MATLAB observation here, the first one, we got the transfer function obtained in part A was converted into state space representation using MATLAB. And second, since the denominator of the transfer function is fourth order, 4 state variable were required. So for the third one, the state space model was represented in a form x dot is equal to ax plus bu and y is equal to cx plus du. That's where we can find the matrix. And MATLAB was used to generate an equivalent state space model and simulate its unit state response. Next one, the unit step response of the step model. Step model is identical to the transfer function model obtained in part A. And last one, we can already verify that both models represent the same electrical network system. The small overshoot and short settling time indicate that the system is stable and has a fast transient response. That's all from me for part B. For the next part, I will pass to my candidate.
Hello everyone and Dr. Hafiz. My name is Mirza Takiwadihan Merabizi. My metric number B122510162. So I will cover discussion and analysis for part A and part B. So moving into our analysis and discussion section, I start with part A, which cover our frequency domain modeling. For first, our derived transfer function is a fourth order system. The reason is a fourth order system is simply because our group circuit has a 4 energy storage element, which is 2 capacitor and 2 inductor. Second, when we test this with this unit step input in MATLAB, we notice the system react incredibly fast. If you look at our command window right here, the rush time is just around 0.000053 seconds, and it's fully settled within 0.000088 seconds. This shows that the circuit responds almost instantly to any input signal. Next, let's talk about how the system handle oscillation and its overall stability. Third, our peak overshoot is extremely low, only 0.1797%. You can see the response graph that the curve is very smooth and it doesn't bounce around. This means the resistor values we use 4 ohms, 5 ohm and 6 ohm give the circuit really strong damping effect that stop any wild oscillation. Fourth, when we check the system stability using this pole zero map, as you can see, all 4 poles are plotted strictly on the left of the S-plane. Since no poles are on the imaginary axis or drifting to the right side, we can safely confirm that our system is stable. Now let's switch over to part B, where we look at the state space modeling. First, while the transfer function from part A is a graph for showing us how the input affect the output from the outside, the state space model changes that. It break down that the big fourth order equation into 4 smaller connected first order equation, letting us see exactly what happening inside the internal component. Second, using the controllable canonical form, we map those internal states into these standard metric numbers A, B, C, and D. All the heavy number you can see this screenshot directly match the numerator and denominator coefficient we calculate by hand earlier in part A. All to wrap up the discussion, let's look at our final verification. Third, when we run the step response simulation for our state space model, the graph we got was 100% identical to the transfer function graph from part A. Every single key value, the rush time, the settling time, and the tiny 0.1797% overshoot. And fourth, this perfect match between the two graphs prove that our math and transformation are completely correct. It shows that whether you use classical transfer function or modern state space method, both ways are mathematically equivalent and perfectly describe how the circuit behave in real life. So that's all from me.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Irsyad bin Nur Azman, number matric B122510198. Today I will explain about the conclusion after we do the project. Firstly, the project successfully derived the analytical fourth order transfer function and its corresponding state space representation for the group 2 network circuit. We do the calculation for the circuit given, then pole 0 analyze proof that all system poles lie strictly in the left half of the S-plane, confirming that the electrical network is entirely asymptotically stable. So after we do the calculation, we get the pole at the left half of the S-plane. After that, we do the MATLAB simulation to verify that the system reacts rapidly to a unit step input, achieving a rise time of 0.00053 seconds and settling smoothly with a minimal overshoot of 0.1797%. The flawless alignment between the transfer function and state space response validate the accuracy of the theoretical formulation and metric transformation. So for the calculation and the MATLAB simulation, we validate the accuracy from the MATLAB and the calculation. And lastly, all core assignment goals were fully met, depending practical engineering experts in control system analysis and software-based verification method. Thank you, that are from us.